So good afternoon, I'm Fabio Del Frate from University of Tor Vergata. I'm going to present some results, some considerations regarding quantitative remote sensing, which means remote sensing focus on the retrieval of parameter, on the estimation of geophysical parameters. We're going to see a couple of examples, one regarding land and the other one regarding atmosphere. So there is always the problem of training data collection in these cases. For land parameter estimation, this can be performed using literal review because there are ground truth campaigns that have been carried out and that have been published. Also, ESA carried out ground truth campaigns where ground truth has been collecting correspondence to remote sensing data. And the other possibility is to use electromagnetic modeling. So radiative transfer models to generate. Here is the sample we are going to see is basically there are backscattering coefficients either at L band, either at L or at P band. Here in the plot you see the L band, taken at three different combinations of polarizations, HH, HV, and VV. We are going to address this problem according to schemes. In the first scheme, which is the problem number 1, we trained the network, the model, with experimental data, and we test it on the experimental data. In the other scheme, we train the network with simulated electromagnetic data, and we test on experimental data. The input is the L band and P band backscattering coefficients together or as a single configuration at HH, VV, and HV polarization. Here is the campaigns that have been used to generate the data. 5 different, you see, campaigns. One also regarding mangroves, the other are deciduous and conifers. And we come up with 108 patterns using this. So 108 input-output examples. They're not that much, so we use a K4 cross-validation procedure, which means to divide the whole data set into 3 subsets with uniform distribution of biomass, and in using 2 of the subsets for training, and to use the remaining one, the other subset, for test, and then to swap these 3 different subsets to come up at the end with the 3 possibilities that have been performed and that of which the results have been averaged. See, are the results for 3 different models: neural network, linear regression, non-linear regression. This is the root mean square error, and you see that neural network has the best performance in terms of root mean square error, but also in terms of positively combining the P band and L band backscattering coefficients. So you see that, for example, non-linear regression gets a better result just using L band rather than using P band, rather than using P plus L band. Why this is not true for neural network? And here is the scatter plot, where you see the true biomass against the retrieved biomass. You see this is very interesting results. Also for high value biomass, which is not trivial because of the saturation problem that we usually have. The other possibility, the other approach, was to use electromagnetic model simulations. So we have to take into account in this case 4 different scattering mechanisms: volume scattering, first scattering, and double bound scattering that are indicated here. We use the Tor Vergata microwave scattering model to generate 171 different values of wooden biomass, but this was also combined with different scenarios regarding the values of soil moisture and regarding the values of biomass density of the understory. So a lot of combinations of these variables, which allowed us to generate thousands of data to train the data. And this is the final result with the root mean square error, which is 4.6 kilograms over square meter using the L and P band. So this is a result obtained training the network with the simulated data and test it on experimental data. Here we see a little bit of the saturation problem, but the general result I think it's interesting and good. So we go to the other case, the atmospheric case. Here, in this case, the parameter estimation is focused on the retrieval of ozone concentrations. In the atmospheric case, you usually have an additional issue, which is the fact that you have many, many inputs, because the spectrometer are collecting the data at thousands of wavelengths. And this, of course, have to be considered to avoid the curse of dimensionality. So besides the problem of training data collections that can be taken using ozone zones or other ground truth data, level 2 products coming from other missions or electromagnetic modeling, you have also to face with this problem of dimensional reduction. We use this. So basically, this is the basic scheme: the radiances as input and the output, the ozone concentration, either at different levels or as an integrated value. Regarding the dimensionality reduction, what you can perform is a feature selection, or better, wavelength selection. How can you do this? You can do this using an extended pruning procedure, so in a very automatic way. Of course, you can also base your choice on physical considerations, but this is a way to perform it in a very automatic way, based also on neural networks. In this case, you are going to check what are the weakest connection after a first training that you have operated on the data, using the data. Then you look for the weakest connection. You remove the weakest connection, and removal after removal, you are going to affect also some inputs of the networks, which means some waves of the networks. These wavelengths are those who are characterized by less information content. So basically, you can eliminate them, you can cancel off them in a subsequent training of the network, just using at this point only the wavelength with the most significant content. The input units with more information content are those which. So this is the process that you can use for the final estimation. You first train the data with the simulated data using radiative transfer model. You come up with a first network. On this network, you apply the extended pruning to select the most important, significant wavelengths, and then you retrain a new network using only the most important wavelengths to come up with a final neural network dedicated to the ozone concentration. Here is an example that we had. Is basically as a time series of concentration estimated either by the satellite using neural networks with two modes, one using only UV measurements, the other one using UV and visible measurements. And the third plot is the plot obtained using ozone zone, so let's say using ground truth. There, you see there is a very nice consistency. There is some bias, basically due to the fact that the ozone zones, of course, are punctual measurement, while the satellite is making a distributed measurement. And just to close, I want to talk about another possibility of performing dimensionality reduction. In this case, it's not dimensional, it's not feature selection, but feature extractions, which means that from the overall vector of radiances, you try to extract the most important content in terms of what are called nonlinear components analysis, which is kind of different from the typical principal component analysis. So you use your input vector, your radiances vector in input, but also you want to replicate this in output. So that if you are able to do this passing through a bottleneck layer, which is inside the network, it means that the output of the bottleneck layer are able to represent all the input vector, and you can use these nonlinear components, the output of the bottleneck layer, to train the network, which then are going to perform the estimation. So this concludes my talk. Thank you very much for your attention.